A good first step in becoming facile with object-oriented programming is to look at some examples. And that's the mission for the rest of this lecture and the next. We've tried to make the examples concrete and use them to show how to structure an object-oriented programming solution. It's not the functionality of each example is all that important. What we really want you to look at is how that functionality was structured. So, as you go through the examples, see what we've done, and perhaps think a little bit about how you would have done it differently. As an example of classes in action, let's define a new data type to represent a set of integers. So initially when we create an instance of that set, the set will be empty. It has no elements in it. And then as we add elements to the set will slowly accumulate integers. We'll have a constraint that we want to impose, which is that we wish that a particular integer will only appear at most once in a set. So if I attempt to add an integer a second time to the set, nothing bad will happen. We just it won't have a duplicate copy within the set. That sort of constraint is called a representational invariant. In other words, it's a property that's true of all instances of the set of integers that we're creating. And that's enforced by the code and the methods. And most representational invariants are there because they're an important part of the semantics of the object that you're trying to create. For an internal data representation, we'll simply use a list to remember all the elements of the set. We're going to define three interface methods. The first one is insert, and it inserts an integer e into the set if it's not already there. If you try to insert it again, we're going to have the code implement the representational invariant above, and it will just return without doing anything. We can test if a particular integer is a member of the set, so this is a Boolean method that returns true if the integer is in the set and false otherwise. And finally, we can ask to remove an element from the set. And now we have a semantic choice in front of us. Choice one is that if you try to remove an element that's not in the set, that would be okay. I mean, you wanted a set without that particular integer in it. There is a set without that integer in it, so everybody's happy. No harm, no foul. Normal execution continues. Choice two is that an attempt to remove something that the programmer thought was in the set probably represents an error. And now is an opportunity to stop program execution and let the programmer debug the situation. And that's the semantics we've chosen. Choice two. Let's go look at the code. Here I have an idle buffer that contains my class definition of int set, which is what I'm calling my new type of object, which represents a set of integers. And it's followed, indented, with all of the definitions of the attributes that I want to be part of the int set class. So let's come over here and type function F5 to read this code into a running Python shell, and let's give it a test out. So I can say s is equal to, let's create an instance of my integer set. There we go. And in fact, if I ask for a print representation of s, it's printing out as sort of the null set. So let's go off and, you can see it's going to give me a list of all the possible methods that are available for the object s. So if I want to go off and insert an integer, I can say insert a 3, insert a 4. Maybe I'll try to insert 3 again. Okay, and now if I go off and print a representation of s, it's a set that contains the integers 3 and 4. So let's look a little bit of the code and see what happened. When I ran my constructor, I provided it no additional arguments because there was no other internal data that I wanted to initialize from the outside. If we go look at what the init method does, we can see that even though it takes no arguments when I called it, and in fact, as I explained earlier, Python will provide the object being initialized as the value of the first argument, in this case, the value of the symbol self. So what the init code does is it goes off and creates a new instance variable, a new data attribute for the instance that's being initialized called vals, and it sets it to the empty list. And so that's going to be the representation of the integers in the set, and initially it has no elements in it. When I called insert, Well, I did it with a single argument, and remember again, Python will take the object that I'm manipulating, in this case the set I just created because I called it s.insert. So whatever the object is that's the value of s is what's going to be passed as self, the value of the self argument to the insert method. And then I provided one additional argument 3, which becomes the value e. So it's going to assume that e is an integer and inserts e into self. So what it does is that it checks to see whether or not e is part of that list. And if it's not an element of the list, it adds it. Otherwise, it makes no change and continues on. And then if I ask to print out the value of s, let's go look at the string method. So remember, print will want a string representation of the object, and this is the method that will create that. So the first thing that the string method does is to sort the elements of the set into numerical order. So when I print them out, they'll sort of appear from the smallest integer to the largest integer. And then it constructs a string which has an open brace at the front and a closed brace at the end. And then in the middle, well, let's figure out what this does. So for each element e in self.vals, I'm going to create a string version of that element e, so a string representation of the integer. And this is all part of a list comprehension, which means that it'll take all the individual calls to the string of each element and make them elements of a list. And then I use the join operation, the join method of a string. So I'm going to say, please join all the elements of this list by separating with the string comma. So that's what this does. So what I would expect to see is an open brace, a comma-separated list of integers, or the string representation of those integers, followed by a closed brace. And that's actually what happened over here. Let's go off and test some of the other operations. So s.member, is 3 a member? Yes, true. How about 5? Let me pause for a moment here. Notice that as I'm typing in a call to a method, if it can, Python will show me, or idle will show me, a tooltip sort of explaining what the arguments are. And the way Python, where it gets an explanation, comes, if I look over here in the code, I can see that what I have is that it takes the first line of the doc string. So this doc string is a string that follows as the first line of any method definition. So I can put a string in here, and Python will print out the first line of that string. As you can see it showing here as the tooltip. So that's a handy way to provide some, a little help to the user of your new object about what types of arguments are expected. Okay, so I can say s.member 5, false. 5 is not a member. So I can go off, and suppose I go off and insert 5 or 6. That's good. So print. So 3, 4, and 6. What happens if I go remove 3? Yes. So I've taken 3 from the set. What happens if I remove 3 again? I get the error. So let's go look how that works. So if we look at how the remove method works, it's going to go off and use the remove method of lists. So it's going to call self.vals, which is a list. It's going to call the remove method of that, and it's trying to remove this particular element, this particular object from the list, in this case the integer 3. It tries that, and what happens is if you try to remove an element that's not there from the list, Python creates an error. And what we're going to do is enclose this particular statement in a try and except clause, so that we're going to basically try to do this, and if we get an error, we'll execute this code. So if the removal was successful, there's no error, and we don't do the except statement. But if there was an error in the execution of this code, we come here. And we chose to basically create a special error of our own, which says that, look, I'm going to create a value error and report to the user that the value integer it was trying to remove wasn't found. If we had chosen instead to ignore the error, that was choice 1 when we were discussing the semantics, here we could have just gone ahead and typed in the word pass, meaning don't do anything, just swallow the error Python created as part of the list remove operation and continue with normal execution.